Hello, everyone, and welcome to Conversations on Ichnology. The International Ichnological Association is glad to offer this lecture series to anybody interested in ichnology. The lectures will take place on the last Friday of each month until November, and we will always try to find a time that works for most people across the world. Thank you for joining us today. And also we thank to the IIA members for their support of our association. The IIA is committed to aiding as many students as possible in participating in ICNIA 2028, and more members are required to make this happen. IIA now offers new member categories, making membership more accessible to everyone. So we invite those who are not already members to join the IAA. About today's talk, James MacEachern is a full professor in the Department of Earth Sciences at Simon Fraser University in Canada. He teaches undergraduate and graduate courses in sedimentology, stratigraphy, and paleontology, as well as short courses and core workshops for private industry. James received his PhD in 1994 from the University of Alberta under the supervision of Dr. George Pemberton. Dr. MacEachern's research focuses on the integration of ichnology, sedimentology, and sequence stratigraphy in order to refine the positional models for shallow marine siliciclastic successions. He has published approximately 140 papers during his career. James is an associate editor for Ichnos and has served as co-editor and associated editor for Journal of Sedimentary Research from 2012 until recently. He has received a number of awards and medals, most notably the Middleton Medal from Sedimentology in 2020 from the Geological Association of Canada, and the Raymond Moore Medal for Excellence in Paleontology in 2023 from the Society for Sedimentary Geology. The ichnology of deltas is the theme of our talk today, which has been received Dr. MacEachern's attention for the last 20 years, I would say, in collaboration with Dr. Karrie Bann of Ichnofacies Analysis Inc, also in Canada, and who is in the audience today. Karrie Bann received a PhD in geology from the University of Wollongong in Australia in 1999. Her thesis involved the ichnological and sedimentological analysis of Permian, marine, and coastal Australian deposits. She undertook a postdoctoral project at the University of Queensland, where she studied the ichnology and sedimentology of marine and coastal reservoir deposits in outcrop and in core. She also worked as a consultant looking at the ichnofacies analysis of various reservoirs intervals in core. In 2003, she moved to Canada to undertake a second postdoctoral position in the Ichnology Research Group at the University of Alberta. During this time, she did further work on the Permian in Eastern Australia and on several shallow marine successions in the USA and Canada. Upon completion of this work, she then set up her consultancy business. In this capacity, she has worked on numerous successions around the globe. Karrie is also well known as an accomplished graphic artist and displays much of her work in a visual manner. Before I give the floor to Dr. MacEachern, I would like to request that everyone close their microphones so that there is no noise interference during the talk. This talk will be recorded and will be available at the IIA YouTube channel soon. So James, now it's up to you.
Thank you, Renata, for a very kind introduction. And it's a pleasure to be here. So I have a number of slides to get through. So with no further ado, we should probably get started. As Renata pointed out, most of the work that I've done has been trying to integrate ichnology with sedimentology and stratigraphy. I am not a formally trained paleontologist. I'm not a taxonomist. I'm actually a sedimentologist who, in completing a PhD with George Pemberton, recognized that in order to really do proper facies analysis in deep time, one needs to know how to wed or integrate trace fossil data sets with well-constrained sedimentology because they relate to one another, they feed back on one another, and they help you to better understand the depositional relationships. So well, it was a bit of a surprise for me to get the Moore Medal wherein it's for a paleontologist. I don't regard myself to be a paleontologist in any real capacity. So dynamic environments are challenging to characterize. And that's because they're overwhelmingly heterolithic. So they're telling you that there's marked variations in depositional style and depositional process. They experience pronounced changes in physical and chemical conditions that vary at a number of different timescales. And as a result, the depositional environments typically show variations in deposition rate, physical energy, substrate consistency, episodicity in deposition, fluctuations in salinity, elevated and variable water turbidity, changes in oxygenation, changes in resource delivery. And the more dynamic those environments are, the more those parameters vary at a variety of scales, some of which might exceed the ability of the benthic community to accommodate. In other cases, settings that are much more prone to stable conditions have, even though there are variations that are operating, they tend to be more predictable and more persistent. I think in terms of, for instance, in a lower shore face environment of a strand plane, you have shoaling waves. Wave energy may vary to some degree during fair weather conditions, but essentially you're above fair weather wave base. You have a substrate that is largely mobile. There's food that is lifted up into suspension. There are stable salinities, and these lead to very different kinds of facies. And the only real pronounced variation that one sees in these settings is the degree of storm influence. So what we want to do then is recognize that these variations in physical chemical conditions lead to changes in the composition and distribution of trace fossil suites, the bioturbation intensities, as well as their distributions, bed and bed set thickness distributions, and of course, the primary physical structures. As a result, there's not a single suite or a single trace fossil characteristic, indeed, not a single primary sedimentary structure that allows you to be able to discern whether or not you're looking at one particular dynamic environment or another. It's the juxtaposition of different beds and bed sets within the facies and the stacked juxtaposed nature of the different trace fossil suites that hold the clue as to whether or not your dynamic environment is persistently salinity reduced, or is it in the open marine realm, but you have other factors operating within the marine realm? Is it evidence of fluvial sediment influx in a delta, things like that? That variation of seeing units like we see on the left here, where they are stable and unstressed, seeing those juxtaposed with beds and bed sets like the unit on the right would tell you that you have these temporal variations within the same environment that are part of that dynamic nature of the setting. So we're going to talk about deltas rather than brackish water bays or lagoons or tidal fluvial estuaries or other dynamic environments. We're going to talk about deltas. If we use Elliott's definition, we would say that it's a discrete shoreline protuberance that is formed where rivers enter some standing body of water and supply sediment more rapidly than the basinal processes can redistribute. In other words, you have a point source sediment delivery, and you have a relatively long-lived area of sustained river delivery or river sediment influx into that part of the standing body of water. For this talk, we're only going to be discussing marine deltas. I'm not going to go into lacustrine deltas and the juxtaposition of Murmia, Ichnofacies, and more continental associations in the subaqueous realm. We're going to stick really to marine deltas. And for that, then, the most common way that we often think about these systems is to use the Galloway ternary plot that tries to relate the main depositional processes that operate at the coast: fluvial sediment influx, wave energy on the lower left, and tidal energy on the lower right. And it's the relative interplay of those processes that largely control the character of the delta that you're looking at. But that ternary plot really stands at the top of a larger ternary diagram of all sorts of coastal systems. And although this is relatively simplistic, it does highlight that the two environments that are most commonly misidentified with one another are deltas and shore faces. And as a result, when you take a look at the broader expression of these coastal systems, all deltas, even river or even wave and tide dominated deltas, are foundationally much more fluvial influenced than any other coastal system, even more riverine influenced than estuaries. And as a result, we need to really recognize that when you're talking about something that is a shore face or a strand plane or whatever, you're talking about a sedimentary environment that's largely divorced from fluvial influence. It's mainly affected by basinal processes, which are overwhelmingly wave energy and storm energy. Deltas are characteristic of prograding coasts. That is, they are regressive deposits, and as a result, they tend to occur when sea level is either falling or when sea level is stable, and allow that sediment delivery to the coast to permit the shifting of proximal facies over distal facies with time. They lie along strike of counterpart environments that are reflective of the dominant processes. So for instance, a wave-dominated delta may be expected to lie along depositional strike of a non-deltaic strand plane or a shore, what I call a shore face. If you're in a more tide-dominated delta, you may very well see it lying along depositional strike of open coast tidal flats. But we have this sense of whatever the prevailing basinal processes are, they're being overprinted by whatever style of fluvial delivery is operating within the delta. And it's that, again, interplay of those two main basinal processes, although I tend to keep wave energy and storm energy discrete from one another. But nonetheless, you have those basinal processes, and then superimposed on them are fluvial sediment influx. And so one should expect then that in any area where you're looking at deposits, that it's not unusual to see deltaic systems pass along depositional strike into non-deltaic facies, and there's going to be a gradation or a transition from one location to the other. When somebody looks at the subsurface or looks at a unit and they say, oh, this is the Cadott Formation, it's a shore face, and imply that there's everywhere in the basin it's a shore face, that's clearly nonsensical. Sediment has to be delivered to the basin somehow, and in almost every case, it's by fluvial delivery. And as a result, those Cadott shore faces pass along strike into Cadott deltas. And then we want to be able to tell when we look at the sedimentary facies whether or not you're looking at the deltaic expression or the non-deltaic expression. So we've talked about the characteristics being dominated by that relative interplay of river sediment influx, wave energy and storm energy, and tidal energy. But there are two other main factors that also dictate what kind of deltaic succession one is going to see and some of the characteristics one will observe. And one is the relative density of the river water relative to the receiving basin. If you're in a lacustrine system, in most cases, flows will be predominantly homopycnal or equal density, with periods of time when the river's in flood, where you might get hyperpycnal or denser river flow, sediment slurries coming into the receiving basin. In the marine realm, you almost never get homopycnal flow unless you've got a gravel-dominated delta and everything is inertial driven. Rather, you tend to see transitions between hypopycnal or flow where the river water is less dense than the receiving basin, and hyperpycnal flow typically during river floods. And we see then the deposits of those two parameters or two factors operating all the time in the sedimentary facies. And then the last parameter is the actual sediment grain size that's being transported by the river. Ice house periods or high latitude systems commonly have coarser grained sediment delivery from the rivers. Tropical rivers, greenhouse periods often have much higher suspended load dominated rivers. And so the sediment grain size making up the bed load and the volume of suspended load greatly impact the resulting sedimentary facies that one sees and the animal sediment responses. We could talk about a whole range of depositional components of a delta, right from the fluvial floodplain to the upper and lower delta plain, the distributary channels, things like that. But overwhelmingly, in the rock record, what we tend to find the best preserved or the most widely preserved are the facies that are subaqueous. That is the part of the delta that is effectively always below low tide and lies seaward of the lower delta plain. That is in the landward or in the more seaward part of the system here in the blue, the prodelta, which forms a depositional platform of relatively finer grain material overlain by coarser grain deposits that occur in shallower water positions that we would normally call the delta front. And because these systems are regressive or progradational, the cycles that we tend to find will show fine-grained heterolithic deposits of the prodelta progressively overlain by more sand-dominated heterolithics and sand-dominated successions of the delta front. Yes, we will see distributary channels, and there are places where you get delta plain, but I'm going to focus most of our facies characterization ichnologically and sedimentologically to the prodelta and the delta front. And so when we see diagrams then that express these vertical profiles, what we tend to look for is in the distal facies, the transitions into these mud-dominated heterolithics that we would say are more characteristic of prodelta conditions. And these will transition upward into progressively sandier, but still locally heterolithic successions that one would place within the delta front. All that put together then would suggest that what we really need to do to assert a deltaic interpretation in the rock record is not the recognition of the basinal processes. That helps to constrain what kind of a delta you're looking at. What's really the diagnostic element of recognizing a delta deposit in the rock record is the evidence that there is direct fluvial sediment influx into that local area. That is, you have a trunk fluvial system that's delivering both suspended load and bed load and all the physical chemical stresses that are associated with that delivery into an otherwise marine basin. And if one can't show that there is riverine influence on deposition, whether you're looking at the prodelta or whether you're looking at the delta front, then you haven't really proven that you're looking at a delta. The hallmark of being a delta is that there's riverine influence on sedimentation and direct, not just that it's supplied to the shoreline and then moved along depositional strike by longshore drift and other coastal processes, that there's actually a point source delivery in one local area. So how do we do that? How do we go and identify riverine influence on our sedimentary facies? So we'll spend some time talking about the classical fluvial signal. The main things that riverine sediment delivery does is it increases deposition rates. It loads the substrates and lends itself to strong and high degrees of soft sediment deformation. It promotes sediment gravity processes, things like hyperpycnal flow from river floods or failures on the delta front to produce delta front turbidites, and overwhelmingly abundant fluid mud that is flocculated, is water saturated, and deposited directly onto the bed, either from surface plumes, buoyant plumes that we would call hypopycnal plumes, or from hyperpycnal sediment gravity flows delivered directly out of the distributary channel. Here's an example from the Muddy Creek, from the Farron Sandstone at Muddy Creek in the Book Cliffs. And we have here with the red arrow pointing to a intrepid graduate student standing at the edge of a failed block of delta front that is foundered down into the pro-delta of that system. We're talking about large-scale deformation. But that can occur at all scales. And so even at the bed scale or bed set scale, we see ample evidence of soft sediment deformation, convolute bedding, loading, overturned beds, etc., that represent the rapid delivery of sediment to the shoreline on top of a fine-grained underlying pro-delta deposit that cannot support that rapid rate of deposition. And we see that then at the outcrop scale, we see it at the core scale. Soft sediment deformation, whether it be convolute bedding, whether it be small scale gravity faults, whether it be overturned bedding, etc., are very common, and they're expressed typically by these deformation features, in many cases making it difficult to identify even any of the traces that are within it. But because of the elevated deposition rate, the higher this degree of sediment delivery from the river, typically the lower the bioturbation intensity. And so the fewer traces there are even to identify. If one gets sediment slurries from river floods, then it's not uncommon to actually get structureless beds that are essentially the A division of boomatocycles, whether they be made up of finer grained silty material or whether they be made up of sand, but these beds are deposited in a structureless state. I have never seen a non-deltaic shoreline, that is a shore face, that has either abundant soft sediment deformation, sediment gravity flows, and structureless beds from sediment slurries. That really is, in the shallow marine realm, that really is one of the distinctive characteristics of riverine influence. Sediment gravity flows, shore faces and other systems like that don't lend themselves to sediment gravity flow because the depositional gradients are just so low. But a delta front has significant slope. And so, and delta fronts also have distributary channels that have jet flow that's coming out of the distributary channel into the basin. And so we then look for the evidence of these turbidites that show episodic colonization, top-down colonization, and typically lower BI values. So sedimentologically, we look for evidence of Buma cycles, Buma A, B, C, D, and E cycles, and then we look for the evidence of marine colonization that are typically episodic, top-down, post-event colonization. Hyperpycnites are a little bit different. They often are thinner, but they also are made up typically of these normally graded, rapidly emplaced beds that show top-down colonization. And so they are another type of sediment gravity flow. Buoyant plumes are widespread. because most river water is less dense than the marine basin. So the suspended load tends to ride as a surface plume that exits the distributary channels. And that high suspended load, the high suspended loads in the river discharge itself can also lead to hyperpycnal flow, like we see here with the white arrow pointing to jet flow of fine grain material outboard of the distributary out into the basin. Here in the Atchafalaya Basin in the Gulf of Mexico, you can see how turbid the water is. And because it's a surface plume, that water, that silt and clay-laden water is banked up against the shoreline by longshore drift and by propagating waves to lead to shallow water positions having quite a high amount of silt and clay in the water column and flocculating and settling to the bed. And as a result, often what we'll find is that even whether you're looking at pro-delta deposits, like we see here that are the more mud-dominated, into distal delta front deposits, they are overwhelmingly heterolithic. The event beds being laid down by either flood discharge of the river or by basinal processes, and the mud mainly being draped over those beds during river floods. Storms in particular are almost always accompanied by precipitation. And so as a result, when one has a storm that might be producing hummocky stratification or swaley stratification, rivers will also be going into flood soon after and delivering large volumes of suspended load as buoyant plumes that then flocculate and rain down to the substrate to drape those event beds. That high frequency draping of the event beds in the basin largely make it difficult for the event beds to be colonized by benthic community. And so we often see lower BI values and lower diversity suites with greater and greater storm and river flood influence. The settling of that fine grain material from the buoyant plumes or from hyperpycnal flow is much fresher than the receiving basin. It has a lot more fresh water in it. And as a result, there's a salinity contrast at the bed between the mud being delivered either by hyperpycnal flow or from hypopycnal plumes and the pore water within the substrate in the marine basin. And that favors then the development of cineresis cracks. And so in these basinal positions in the pro-delta and the delta front, where units are fairly muddy, we will find cineresis cracks. And what's really then distinctive of being in a basinal position is to find open marine, or at least traces that are positively correlated to more open marine conditions like Zoophycus or Phycosiphon or Astrosoma or Chondrites, juxtaposed at the bed scale with units that have cineresis cracks. So these are telling you that there are short-lived intervals of time when you had salinity fluctuations and salinity reduction, and other times where you have normal marine salinities. And again, I've never seen in either estuarine systems or in shoreface systems that juxtaposition between salinity variation and fully marine trace fossil suites. That is, to my mind, a strong indicator that you're looking at fluvial sediment influx into a marine basin. You get a lot of phytodetritus, and so we see a lot of carbonaceous debris, either as particulate matter draping event beds, what are called phytodetrital pulses, like we see here, or there are mudstones that drape event beds are overwhelmingly dark and carbonaceous because the mud is coming from the river, which is coming from the terrestrial land surface. The mud is rapidly deposited, and so the mud is generally shows very low BI values. And then so when we start looking at the ichnological responses, we tend to find that because of this combination of physicochemical stresses linked to fluvial discharge, we tend to find that bioturbation intensities are markedly reduced. They are variable, but variable at the lower ends. BI 0 to 3 are more common and typically less than 2 with greater and greater proximity of fluvial discharge. Most of the traces are reflecting burrows of mobile deposit feeders, sessile deposit feeders, detritus feeders, navichnia or sediment swimming structures in the fluid mud, and some surface feeding structures like piscignus and other feeding strategies. High frequency episodic emplacement of event beds also lends itself to reequilibrichnia, that is, traces that reposition themselves as a function of deposition. When I was first brought to this outcrop area of the Wall Creek in Wyoming, I was told that these beds were assigned to Milankovitch scale cyclicity. But if you take a look at this structure, you'll see that the same trace fossil made by a single trace maker has reestablished itself 6 times over this meter interval. And so this stacked Roselia is telling you that within the lifespan of one trace-making organism, there has been more than a meter of deposition incrementally on the seafloor. And that really is a delta story. We see that with the crowded Roselia ichnofabric or stacked reequilibrated Roselia. Here the muds are light colored because they're not oil stained. The sand is dark. And you can see that there are abundant reequilibrated Roselia telling you that those trace makers had to reposition their burrow multiple times during their lives. And when you take a look at the chord example here, you could easily assign all of this deposition to the lifespan of maybe 5 or 6 trace-making organisms. It really is a much higher deposition rate that we just don't see in most other shallow marine environments, bar submarine fans that have very different styles of deposition. Water turbidity is another stress, and as a result, what we tend to find is a suppression of filter feeding behaviors of trace makers and an overwhelming dominance of deposit feeding. And so what we tend to find then is abundant Roselia, Macronychnus, Planolytes, Tychicnus, Thalassinoides, Cylindricnus, at the expense of classical filter feeders like or filter feeding structures that we might assign to things like Scalithus or Praedichnia, like Conychnus, those sorts of permanent dwellings that rely on the food to be delivered to them. High suspended load really is a problem for filter feeding organisms. And so we tend to find that even in sand dominated units, like we see here on the right, virtually all the traces that you're encountering are made by organisms that are deposit feeding in one style or another. So that's the river problem. What do waves do? Well, wave energy, if you talk about fair weather waves, they really don't do anything in the pro-delta because that lies below fair weather wave base. But it does mitigate a lot of the salinity stresses and other factors that the rivers are imposing to the shoreline. It's the delta front where we really begin to see the wave domination or wave influence play a role. What we tend to find very quickly is that sedimentation rates tend to be a little bit lower, and we tend to see much higher bioturbation, although it's still sporadically distributed. And what we begin to really recognize is that even in these sand-dominated and heterolithic units, virtually all traces still remain deposit feeding rather than filter feeding, because wave energy is actually a problem for keeping that suspended load banked up against the shallow part or shallow water part of the delta. Right, under short phase systems, there's lower suspended load. It's moved by longshore drift. It's moved by return flow from orbital flow beneath propagating waves. And it doesn't really impact the shallow water realm to the degree that a delta does. But because the mud is in a buoyant plume at the air-water interface, propagating waves tend to hold that mud zone close to the shoreline. And so in sandier parts of the delta front, there is still elevated water turbidity that filter feeding organisms just don't handle very well. So you then look for that evidence. You look for instance, in this facies here, the fact that all the traces are deposit feeding, There's evidence of escape structures, etc. And then you look for these dark, organic, rich fissile mudstones interstratified with it that have a very low BI, which is probably telling you buoyant plumes being deposited or depositing fluid mud. And when you get to the sand-dominated part of the system of the delta front, that's where it becomes challenging because you're relying on one of the more dangerous approaches of the absence of something telling you something about the environment, right? It's not that Roselia isn't common in shallow water sandstones or ophiomorpha or siphonicness or things like that. You do expect them there, but you expect them to be accompanied by structures positively correlated to filter feeding. And after looking at a number of cores or a number of outcrop areas, you may begin to see that you actually lack those traces reflecting filter feeding strategies. And so that then would be used to possibly suggest then that you're looking at elevated water turbidity. In my experience, because the pro-delta tends to be dominantly depositional zone, the pro-delta is the best place. Those facies are the best places to look for the evidence that you're on a delta. Delta front can be challenging to differentiate from a shore face, particularly in a more storm or wave-dominated system. Storms have a major impact on all coastal margins, and many wave-dominated deltas are also show a strong storm signal. But really, every delta type, river-dominated and onward, tide-dominated, etc., can have storm deposits. And so one shouldn't be surprised to see hummocky cross-stratification or swaley stratification interstratified with your proximal pro-delta and delta front deposits. The problem is when you have very, very high storm energy so that you have nothing but erosionally amalgamated tempestites. If you are faced with units like this, where you have nothing but erosionally amalgamated HCS, there's no basis in here for telling whether you're looking at a delta front or you're looking at a shore face, because you're not preserving any of the fair weather beds, nor are you preserving the record of river sediment influx. You're simply seeing full reworking of that substrate episodically by successive storms. So the stronger that storm energy is, the more it'll obscure the deltaic signal. And when, that's why for many workers, they look at units like the Kenilworth, and because it's storm dominated, they've always called it a shore face. But I would call your attention to these lower units in through here, wherein those tempestites are interstratified with fluid mud, and we have evidence of load casts and failure of the delta, of what I would call the delta front, down into those heterolithic beds. And even within the stacked tempestites in here, there are mud interbeds or mudstone rip-up class telling you that those tempestites were draped by fluid mud in a delta front environment and not a shore face, right? But it's the record of those mud drapes, those fluid mud drapes, that are the evidence that the tempestites are occurring in a delta as opposed to a shore face. So this is what the pro-delta tends to look like for these storm-dominated systems. You see the wave-generated and hummocky stratified and micro HCS stratified sands, and they are draped by carbonaceous fissile mud that have a very low BI value. And that mud often has syneresis cracks, telling you that there are salinity fluctuations during the emplacement of that mud. And that is a delta story. That is really a good indicator that your tempestites are occurring concomitantly with the delivery of a suspended load. And that's because in a delta system, storms are generally accompanied by precipitation. And precipitation, elevated precipitation, leads to river discharge that carries the suspended load out to the delta front. And that mud then can flocculate and settle out onto those event beds, giving you that heterolithic expression. Tidal processes are a little bit different. You're looking for tidal rhythmites, various types. We see tidally bundled crossbed sets here with Jonic Bhattacharya, my good friend here for scale, in the Fruin Sandstone of Utah. We look for those current generated bed forms, but we also look for the pro-delta cycles to be markedly heterolithic. And that heterolithic character is overwhelmingly dominated by, again, fluid mud that is carbonaceous and doesn't really lend itself to very high bioturbation. The more the fluid mud is in place, the more the system tends to have a very low BI value. And it was as a result, then we see organic rich, laminated, and fissile muds draped over top of either graded beds or combined flow rippled beds or tempestites, etc., and low BI values, generally with top-down colonization. In my experience, these tide-dominated deltas tend to have the lowest bioturbation intensities and diversities next to a river-dominated delta, simply because of that rapidly emplaced fluid mud, which is so difficult to colonize. And even in the sand-dominated system, we see current-generated bed forms that are produced from the bed load of the tides, but they are routinely overlain by laminated and fissile muds, locally with syneresis cracks and a very low BI value. And in fact, in these sorts of systems, what you'll find is that when you pause deposition, you end up showing that you're in a fully marine environment and you've got a high diversity suite and high intensity bioturbation. And as soon as the system begins to prograde again, BI values go down and you have very, very low diversity suites. And this is not uncommon for these systems. And so really it's finding those pauses in progradation that's a good indicator that these sorts of deposits that reflect the more progradational state of that delta lobe is occurring in a fully marine environment. All right, so then the models. Well, we use Xylocarian models, Xylocarian Ichnofacies models, as the equivalent of a facies model, not as some do as the particular suites. As I said, you can't go to any individual environment, like a dynamic environment, and find some recurring or persistent single suite that tells you all of the processes that are operating in the environment. So instead, we build these depositional models the way we would build a facies model, using multiple examples, looking at all the trace fossil characteristics, ichnofabrics, BI values, distribution trends, trace fossil diversity, and we find what is recurring, what is persistent within that environment from all the number of examples that we see. We remove the unique, discrete things from individual case examples, and we find out what are the characteristics that all of them have in common. And from that, then we build a model and we use it that we use a facies model as a norm for comparison. We use it to integrate our observations, and then we use essentially a facies interpretation equation to wed those physical observations with the behavioral impact or implications of the traces, tearing positions, bioturbation intensities, etc., to come up with a depositional interpretation. Using mixed river and wave influence deltas, Karrie and I proposed two new ichnofacies that capture the range of dynamic processes that operate in the pro-delta and in the delta front. And the reason we used a mixed river wave influence delta complex for that is because you see a nice balance between the stresses imparted by river sediment influx and the evidence that you're seeing that river sediment influx occurring in a fully marine environment. And as a result, by looking at those juxtaposed beds and bed sets, you can see the nature of the riverine influence on an otherwise marine benthic community. So in mudstone-dominated heterolithic bed sets with sporadically distributed bioturbation, you're seeing juxtaposition of low diversity suites that are dominated by facies crossing elements, both in the sands and the muds, that are alternating with specialized and fully marine associations. And then you look for the other evidences, syneresis cracks, fluid mud drapes, and things like that. This is what we use to define the phycosiphon ichnofacies. And those facies tend to look like this, right? Heterolithic bed sets, you see temporal variations in the processes. You have wave-generated processes operating. You have graded silt to mud drapes over top of them. You have syneresis cracks telling you that there's salinity fluctuations. But you also have fully marine structures like zoophycus. You have there and in through here. You have phycosiphon. You have chondrites locally. And then facies crossing elements like planolites and tachycnus and the like. And so you're having to explain how you get both those specialized structures positively correlated to fully marine conditions alternating with evidence of physical chemical stress. Right? So we see these sporadically distributed marine suites. We see vent beds that are unburrowed, and if they are burrowed, they're cross-cut from higher levels by deeper tier structures. We see laminated or graded mudstones that have essentially expressions that are devoid of burrowing unless they are post depositional, coming again from mid-tier and deep tier structures. And this evidence of salinity reduction, and we use that then to characterize the phycosiphon ichnofacies. And we would interpret that as a storm and river flood dominated part of the pro-delta. Roselli ichnofacies we use for delta fronts, dominated by sand-dominated or characterized by sand-dominated heterolithic bed sets. Again, highly variable BI values, but typically less than or equal to 3. We see low diversity suites that are dominated by facies crossing elements, alternating again with specialized structures that are positively correlated with fully marine conditions. We also see that heightened deposition rate or episodic deposition being expressed by reequilibrychnia of various types. And we see a paucity of filter feeding or suspension feeding related structures, and instead a predominance of deposit feeding. And so we might then look at a facies like this and say, okay, well, what do we see here? We see event bed deposition that in this case are tempestites. We see opportunistic top-down colonization of those beds with shallow and mid-tier structures. The suite is marine, but they're dominated by the dwellings of deposit feeding structures or by mobile deposit feeding structures. We see rare dark mudstone drapes that are only cross-cut by mid-tier structures like chondrites or planolites. And otherwise, this juxtaposition of BI 1 to 4 at the bed and bed set scale that we might interpret as a storm-influenced delta front. Finally, there are departures from that, and that is going to always occur when you're looking at a delta that is not a mixed influence system, but instead is a expression that is the result of the prevalence of one process over the other. Right? Remember, the ternary plot that we have for deltas can show river-dominated, wave-dominated, and tide-dominated expressions, or storm and river flood-dominated. If those processes overwhelm all the other processes, then the archetype begins to fail. In a river-dominated expression, you have much higher deposition rates. You have a lot more soft sediment deformation, sediment gravity flows, and all of the other physical chemical stresses that are imparted by river sediment delivery. As a result, as your BI values go down and as your diversities go down, it becomes harder and harder to assign it to an ichnofacies. Doesn't mean you can't tell that it's a delta, but the archetype, the phycosiphon ichnofacies or the Roselli ichnofacies designation may cease to have application because the trace suites are just too low, or are not balanced between the basal processes and the river processes. And so facies begin to look like this, become harder and harder to assign. Obviously, ones like you see here in A are much easier, but it's a lot harder to assign examples like you see in the pro-delta of either C or D, unless you find them interstratified with units like this. Likewise, you can't assign a unit that's unburrowed to an ichnofacies. Right? So if you have depositional units that are overwhelmingly unbioturbated, they might still be in a pro-delta, they might still be in a delta front, but the application of the ichnofacies concept ceases to have any relevance. In the tide-dominated, we have the same sort of scenario. Pro-delta and delta front positions now will mainly show current-generated bed forms. You'd be looking for tidal bundling. But again, we've already seen that in these systems, BI values are typically quite low or very low, particularly when the system is prograding. The environment is pretty stressed, and there's low diversity suites, and fluid mud is overwhelmingly abundant in the pro-delta, in the delta front, and indeed even in the distributary channels. And so as those stresses become greater and greater, the deposits may very well mimic a persistently brackish water environment that you would otherwise interpret as an inshore river or sort of tidal fluvial estuarine system, because you're not seeing the fully marine signal. So facies like this, when you see units like we see in C, or you see units in D, you can see that those are being deposited in a fully marine environment, or here in F or in G. But it's harder when you look, for instance, at the delta front in A, B, and C, when you have traces like that. None of those traces would be impossible to find in an estuary. So you would be hard-pressed to know that the Teichichnus ichnofacies or some other ichnofacies isn't a better fit for those observations. There's nothing about the trace fossils that say this is Deltaic. It's the physical structures that give you that story. And finally, the storm and river flood model. Well, storm-dominated successions are, again, heterolithic in the pro-delta because they're both depositional and erosional. So in the lower part of the cycle, you should expect to see tempestites that are routinely draped with fluid mud. And that's a great indicator that you're probably in a pro-delta of a deltaic complex. But as your tempestites become increasingly erosionally amalgamated and the BI values go down, again, it might be hard-pressed to tell that you're in a delta rather than in a storm-dominated shore face. And my recommendation is to take a look at what these more proximal facies overlie, because if these deposits are amalgamated tempestites, then your pro-delta should have that highly heterolithic look and low BI values and things like we see here as being characteristic of that facies. Whereas if you are in a storm-dominated shore face, these units in here will typically have tempestites alternating with units showing bioturbation indices of 5 and fully marine trace fossil suites. The wave-dominated model is by far the hardest to tell from a shore face because it has the lowest fluvial sediment influx, the least fluvial impact on the shoreline. And so without having river flood deposits or fluid mud drapes or things like that, you really are only relying on water turbidity as the main evidence that you're in a delta rather than a shore face. And that means recognizing that there's a large paucity of filter feeding behaviors in the sedimentary facies. But just on its own, units like these would be hard-pressed to say this has to be in a delta front. They are, but it's because they tend to be overlying pro-deltaic deposits where you see a little better evidence of that river sediment influx of fluid mud and elevated deposition rates and things like that. Here, the main sand bodies being deltaic is largely linked to what it overlies and the absence of filter feeding strategies, and then the rare fluid mud drapes that we tend to find locally interstratified. But those fluid mud drapes can be moved a long distance along depositional strike. And so adjacent shore faces can receive some of that buoyant mud from river floods. So the mere presence of a mud drape within your shallow marine sandstone doesn't mean that you are in a delta front. You could just be along strike of an active delta front. But this is very different from the classical shore face environments, where the typical expression, it looks like this, where we just see that in the offshore environment, you have uniformly distributed bioturbation, high intensity bioturbation, high diversity bioturbation, interstratified with tempestites, just as we see within the shore face. Storms can modify all that, but in the final analysis, the real differences are this, right? If you see this, you're not putting that in a delta. If you see this, you're not putting it in the offshore, right? If you see units that have pervasive bioturbation like this, it's more likely to be in a shore face. Whereas if you have intervening mud drapes and a paucity of filter feeding and predominance of deposit feeding throughout the thickness of your sand body, chances are you're looking at a delta front. So I normally would have gone through this in detail, but I'm going over time. So let me just say, in general, river influence is really diagnostic of being on a delta within a marine environment. You're looking for these combination of stresses being expressed within your facies. Wave energy tends to mitigate a lot of those, but it can't mitigate water turbidity because it banks that turbid mud up against the coastline. So that's a key indicator. Storms affect all deltas, and they tend to have a close linkage to river floods because storms are accompanied by precipitation, and that is the underpinning of the storm and river flood dominated model. The more storm dominated the delta you have, the more you have drapes of hypopycnal fluid mud. And tides, well, tides move fluid mud everywhere, both as suspended load and as bed load. They have a lot of soupy substrates. They drape over sand bodies, and as a result, they don't really tend to be intensely or thoroughly colonized via bioturbation, at least in my experience. And so the ichnological signature then is lowered BI values, sporadically distributed traces, lots of event beds that are unburrowed, some size reduction, particularly if there's lots of carbonaceous debris and reduced oxygen. I didn't have time to talk about that. Re-equilibration structures, and for me, it's the juxtaposition of these stressed suites with fully marine suites that are the best indicator, and the suppression of filter feeding behaviors in otherwise sand-dominated facies. And these form then the two proposed ichnofacies that Karrie and I have published. And again, none of this work could be done without these very generous collaborators that we've had, and funding from, and for at least for me, from NSERC. So there's not much time for questions, but any questions?
Thank you, James. Great for this great talk. Maybe we can have some time for just a couple of questions, short questions.
Well, if people have time, I'm around for a while. I don't have my exam until noon, my time. So, if we want to do 5 or 10 minutes of questions, that's fine with me. It's not like I have to rush out the door. It's really the audience, that their time, that's important from that perspective.
So I cannot see if someone is raising their hands.
Well, I can't see any list, so I need people to either ask the question or somebody to recount if it's in the chat or something. So I don't actually see any of that here.
Let me see. Not in the chat. Yeah.
I see two in the chat.
Yes.
All right.
Yes, there are now. Is there no way of differentiating between SSD and biodeformational structures?
Yeah, there are ways. What I think what I was trying to get across is that the soft sediment deformation itself will have a tendency to deform any biogenic structures that are in the facies, making it difficult to tell that actually there are burrows in there. It's convolute bedding and loading and things like that. You generally need, well, three-dimensional views. Chorda, it makes it difficult to tell. But if it's a biodeformational structure, that tends to have, well, depends whether you're talking about escape or whether you're talking about sediment swimming or whether you're talking about just the disruption of the bed by the activity of burrowing. But most structures produced by decapods or by polychaetes or bivalves tend to be more tubular, but branching burrows, tunnels, things like that tend to be tubular features. The zoophycas tend to be in planes with the spriton, etc. And those morphologies are more predictable in 3 dimensions, and soft sediment deformation doesn't have that. They're much more irregular morphologies that are more, but in two dimensions, it's possible to look at, let's say, a load cast and misidentify it as a planolites or something. Or a thalassinoides fill, you'd need to see it in 3 dimensions to be sure, I would say. How does coal event beds fit the Deltaic classifications? I'm not really sure what's meant by coal event beds. You mean the phytodetrital pulses, the coalified debris that is transported with the suspended load? If that's the question, it is again almost always either hyperpycnal, that is dense sediment gravity flow transport, and it's in the finer grain part of that sediment gravity unit, or it flocculates with the clay, or sorry, it is captured in the flocculation of the clay and the buoyant plumes, and so that carbonaceous debris is brought to the bed and can result in those mud layers being much more organic rich, or you get a lot of particulate carbonaceous debris concentrated at the tops of beds. And one of the factors of those carbonaceous debris concentrations is that as they oxidize, they can deplete oxygen in the pore waters of the substrate and immediately above the bed, so that you can have these short-lived periods of reduced, not anoxia, don't get me wrong, not anoxic, but they do deplete oxygen near the bed, and that can make it difficult for colonization until those coalified horizons are buried. But it is all particulate. It's not like a coal in the sense of macerals that are resulting from a swamp or from vegetation growing in place. These are all transported terrestrial organics as particles that are relatively common in these deltaic systems. Does that answer your question?
Actually, James, I have a question.
Sure.
No, I was wondering how frequent or how common is to find the pteridolitis ichnofacies associated with the delta from deposits, especially from the Cretaceous, since the Cretaceous, it's not common to see in the literature, nothing discussing about it, but I remember when we have the ichnofabrical workshop in Canada, that we visit some deposits with the pteridolitis ichnofacies, and it was apparently associated with this very shallow deposits impacted by deltas. In your experience, how often you see it, or how seldom, and if you have an idea about how to explain.
Okay, well, the ichnogenous pteridolites is not uncommon if you have lots of wood being deposited in the delta, but of course that's not the ichnofacies because it's not part of a mappable construct that represents a depositional horizon or a depositional environment wherein that substrate was colonized. It's simply a allochthonous transported material. The pteridolites ichnofacies, if one's going to see it, in my experience, occurs in the delta plane only. And it occurs in the delta plane where the lower delta plane, where you have the intertidal part where there's saline conditions, it has overrun and moved landward across the upper delta plane during transgression. So generally, this is where you either autogenically see lobe switching and abandonment of a lobe so that the depot center shifts away from that area and then continued subsidence in the old delta location allows the lower delta plane or marine conditions to overrun what used to be terrestrial so that the old swamps or the forests or whatever are drowned, and then you can colonize that horizon, or wave erosion can concentrate wood like logs, etc. Chuck Savard has log ground model for accumulating large volumes of dead trees in one area and then have the upper surface of those logs colonized as that substrate continues to be drowned. That's one way, or from allogenic transgression. That is where you have stopped overall normal regression and the entire shoreline is retreating. And so you end up with open marine deposits sitting on top of what used to be the delta plane. In my experience, those are the only places in a delta where I actually have ever seen the ichnofacies, not anywhere in facies that were originally deposited subaqueously. I only ever see allochthonous wood material in the delta front or pro-delta areas. And while they can have pteridolites borings in them, they are allochthonous fragments, and it's not clear where they were colonized as driftwood or something like that. But I admit I haven't seen that much. Right? I'm just saying, in my experience, that's where I've only ever seen it.
Yeah, well, you have much more experience to see delta deposits than us, so it's really, really good to know about your experience. Thank you very much.
It was a
James, we
pleasure.
have two more questions in the chat.
Okay, let me have a look here.
How do bioturbation indices correlates with sedimentary facies in deltaic environments, and what are the limitations of using trace fossils for interpreting deltaic environments, and how can this be mitigated?
Well, do we have another 50-minute lecture time? Those are very perceptive and difficult questions to answer. And I would say the first obvious one is that bioturbation indices, if they are uniform or homogeneously distributed in a facies, then I don't think there's good evidence that there are physical-chemical stresses being generated by, let's say, river discharge or any other mechanism. So if I see facies that have a high BI value and those facies are uniformly, let's see, I just go back here. So here on the left, if I see a facies on the left here, whoop, how'd that happen? Come back. There's nothing in that that's going to make me say that there's any environmental stress. And there's nothing in that facies on the left that would tell me, oh, there is an active delta in this area. Because you could go through meters of pervasively bioturbated units that tell you that deposition rates are stable, deposition rates are uniform, and environmental conditions are entirely unstressed. So what I'm looking for in step one is a set of facies wherein the BI indices are variable, that I have evidence that there are multiple processes. That would be the first step I would use. Then I would look at, well, where are those variable BIs? What are they linked to? What layers have high BI versus what layers have low BI? So if I look at a unit and a fine grain deposit that you would otherwise normally say, oh, that's low energy and suspension sediment settling in a marine environment, then I expect that that bed should have a BI of 4 or 5. But instead, that has a BI value of 0. Or maybe, well, in fact, its BI is 0 because in essence, the zoophicus that's cutting across the top of it is coming from a much higher level. So when that mud was laid down, it was not colonized at all. So then that tells me, well, then that mud can't have been slowly deposited from suspension sediment settling. That mud had to be rapidly deposited, or that mud has to have some other underlying stress that precluded any organism from occupying that substrate during its deposition. So in an anoxic or a dysoxic environment, you could do that, but you wouldn't expect normally graded layers like this from silty mud up into carbonaceous organic rich mud. And you wouldn't expect syneresis cracks within it for a mudstone that is indicating anoxia or dysoxia. You probably want to say that mud was rapidly deposited from suspension and that it actually had a lower salinity than the surrounding seawater that facilitated syneresis crack development. Right, so that is a depositional stress that is suggested by the bioturbation indice being that low within a mud. And so I kind of use those as my mechanisms when I'm looking at BI, is how uniform is the BI range, or how persistent is the bioturbation, how sporadically distributed is it, and then to what beds are the higher BIs and the lower BIs related, and how do I explain that? And when those come into play to allow me to say, well, these are the kinds of stresses that you get from river sediment influx, then I'm going to lean on the deltaic interpretation. You could get that in a brackish water bay or an estuary or whatever, a lot of those characteristics, but you wouldn't get zoophicus and phycosiphon and astrosoma and traces like that in an environment that is characterized by persistently reduced salinity. So you would have to explain the units that do have higher bioturbation indices and higher diversity in the context of occupying the same, because these are varying at the bed scale. So you're not changing the environment as you go from one bed to the other. You're changing the depositional processes and the depositional conditions temporally within the same environment. You're looking at the time averaged history of all of the processes that are accommodated by that one environment on the right. And so you have to have open marine conditions that give you specialized traces juxtaposed with highly stressed conditions that don't allow those behaviors to operate. And so that then leads to that interpretation. And that again then would answer to a degree your second question, the limitations for interpreting it. Trace fossils are fantastic when you have them. But when you have low BI units and you have very, very low diversity, and when the diversity that you have are made up of organisms or made up of traces that are all facies crossing elements, you don't have a basis for knowing where you are depositionally. All you know is that the environment is dynamic. But if I have a facies like you see on the right, but it doesn't have zoophicus or phycosiphon or chondrites or astrosoma in any of the beds, I wouldn't be able to say that's deltaic because you could just as easily put that in a brackish water bay, right? Where the dominant stress is salinity reduction, because that's also a place where riverine suspended load is transported into a brackish water standing brackish standing body of water that lets the mud flocculate and settle to the seafloor or to the bay floor or the lagoon or whatever. And it's going to look identical from a physical characteristic. And if all your traces are facies crossing, then you don't have a basis for knowing whether it's marine deltaic or brackish deltaic or just estuarine bay. You have to look at all of the other physical sedimentology within the facies to make that assertion, I think.
Thank you, James. Sudipta?
Yeah.
Yeah, am I audible?
Yep.
Yeah.
Hi, James.
Hi.
Very nice talk.
Well, it's very nice to actually get a chance to meet you. Seen your work, I've seen your papers.
Yeah.
I've never had a real chance to chat.
Yeah, last time we, I think, chatted in Calgary.
Yeah, that was a while ago.
So, how much low salinity can the roselids and cylindric nits can sustain? Can it go all the way up to um, like river-dominated, tide-dominated interval of the alluvium? Can it go interior into the continental realm? So that's one part of the question. And another part is there any latitudinal influence on the trend that you have just described?
Let me think. For Roselia, I have never seen it in very low salinity environments. It definitely goes into the brackish for sure. They do tend to be diminutive. But they re-equilibrate. I see them in estuarine bays and lagoons, and well, as long as the lagoons are leaky and there's some reasonable exchange of saline water and it's not too low on oxygen. I don't think I've ever seen Roselia in a tidal fluvial part of a delta or a tidal fluvial estuary where you have very low salinity and marked fluctuations in salinity. But I haven't worked those deposits to the degree that my colleague Murray and Shaheen Dashgard and many others have done. So I don't want to say you wouldn't get it there. The few that I've looked at, I haven't seen it that far landward. I think but it's definitely a relative facies crossing component provided you have sufficient salinity. Now, from a latitudinal perspective, I probably would have to say I haven't worked globally in the modern or globally in the same time period. So to see high latitude and low latitude of the same time period. But we have, in the case of Karrie with her work, we have worked in post-glacial high latitude facies, and we've looked at greenhouse and low latitude periods where they're much warmer and much more tropical. And generally, when you're in the subaqueous part of the system, we don't tend to see any marked variations in the kinds of trace fossil suites that we get. There are differences in sizes. That probably has to do with oxygenation, metabolic requirements of the trace makers, and how hard it is to be a large animal in an environment where there's lower dissolved oxygen, like you get in warm water versus very cold water. But when I look at Karrie's pro-delta and offshore deposits, I see exactly the same trace fossil genera for the most part that I see in the Cretaceous in the Western Interior Seaway. The facies are good counterparts. When I see the Jurassic in Norway, when you look at the Nisa or the Heather or any of these other ones in the Brent group, the pro-delta stuff looks similar to the pro-delta stuff we see in the Cretaceous or we see in the Permian, with barring certain genera that just don't show up in pre-Mesozoic time or in post-Paleozoic time. So we get stuff, Scalicia and Ophiomorpha and things like that in Jurassic and younger, and we don't see that in Karrie's Permian units. But barring those evolutionary uniquenesses that we find, I don't see market changes in the suite. Karrie might be able to speak more eloquently to that than me, because she's had greater wealth of experience in cold and warm climate facies. I don't have to put you on the spot, Karrie, if you don't want to respond.
Yeah, thank you.
Yeah.
Thank you. We have one last question. How do anthropogenic influences affect modern delta ichnology?
Okay, I'm definitely way out of my depth here, but I think it's a fascinating topic, and something that I would really like to see neo-ichnologists working on. I know that Shaheen Dashgard has graduate students currently looking at microplastics and their impact on bioturbated fabrics and things for certain environments. But all the other stresses, things like fertilizers and heavy metals and all those sorts of things, I don't know that anyone's worked on how that is impacting the benthic communities from the perspective of their bioturbated or bioturbation fabrics and prevailing structures. But I think we shouldn't be surprised that in the future, in the rock record, that the record of our impact on these environments will very nicely show up as being unique to the Anthropocene, as things that we just don't see in pre-human pollution time periods. I just don't know what those would be. Again, Shaheen, Murray Gingras, I don't know why the name is escaping me, but a number of other neo-ichnologists working in the shallow marine realm presumably would be much better suited to answering that kind of a question.
Well, thank you, James, again. Thank you, Karrie, too. We have a message for Karrie in the chat, too. Well, thank you, everyone, for being here. Please remember that we will upload this talk on our YouTube channel, probably next week. And we are going to provide the information about our next talk for May as soon as possible when we have all the details. So thank you very much. I don't know if Renata, do you want to say anything else?
Just to say thank you to James to be here and share all this amazing knowledge with us. It was, this is our second talk, but it's by far the most populated in the room. So thank you very much for your time and for share with us all this to make a kind of synthesis. It's not easy to make a synthesis of more than 20 years of research. So it was really a big, uh, I think that was a gift for the International Ichnological Association and for those that are in the room with us. Thank you very much. And thank you, Karrie, for being part of this.
Now, my apologies for going over time. I really thought I'd fly through more of it, but
It was great.
No
So
worries.
thank you,
Well,
everyone.
I have to quickly eat my lunch, and then I have to go and sit a 3-hour final exam. So I will bid you adieu and go about my business.
Thank you, James. Thank you, everybody. And we hope to see you in the next talk.
Okay, thank you.
Bye-bye.